Hello again all! Welcome back to the Knowledge Tower, where we investigate the science behind the Bionicle legend. For today's investigation, I am going to start off with a simple hypothesis, one that I intend to prove to you all as an indisputable fact by the time this video ends. That hypothesis is as follows. Takua is completely indestructible. He cannot be killed. He can't even really be hurt in any way that matters in the long run. This wandering Matoran turned Toa of Light is able to shrug off anything you throw at him, and this is a fact that was proven to us without a shadow of a doubt in his very first adventure. This is not just simple plot armor, the ability of protagonists within a story to always somehow come out on top when facing dire straits. No. Takua has demonstrated a feat of such ludicrous survival against such unimaginable odds that the only sane conclusion is that he must simply be an immortal being. That is the only explanation for how he could possibly survive the summoning of the Toa to Mata Nui, and I'm going to use a hefty dose of real-world physics to prove it. First off, let's get some context for the main event that is acting as the core of this argument. In the final cutscene of the Game Boy Advance game, Bionicle Quest for the Toa, Takua, having gathered the 6 Toa stones throughout the course of the game, places them around the Mata Nui storytelling circle at the Kini Nui Temple. This activates the energy within the stones, sending a beam off into the sky that summons the canisters carrying the Toa Mata to the island to begin their quest to defeat Makuta and awaken the Great Spirit. This sky beam has the secondary effect of launching Takua high into the air, sending him flying across the island to crash land on Tawahi Beach, where he will awaken to find an empty canister and begin the events of the Mata Nui Online game. We as Bionicle fans do not talk anywhere near enough about how insane this sequence of events is, and how truly incredible it is that Takua not only survives this experience, but also walks away from it completely unharmed. Well, physically anyway, as this event does admittedly leave him with what proves to be the 3rd case of total amnesia that he has experienced so far in his life. To prove just how incredible this feat of survival was, and why it proves that Takua has a durability on par with the strongest of the heroes of fiction, let's break down these events piece by piece. First up, let's look at the massive distance he was thrown here. Both the locations of Kini Nui and Tahu's landing on Tawahi Beach are clearly marked on the official map of the island of Mata Nui, so we know the exact start and end points of Takua's little jaunt through the atmosphere. We also know the size of the island thanks to the official figures given in this inset in the map, therefore allowing us to directly measure the distance between these 2 points. As we have covered before on this channel, the island of Mata Nui officially measures 357 kyo in length. A kyo is equal to 1.37 kilometers, which makes the island 489.09 kilometers long. Counting the pixels that make up the length of the island on this map therefore gives us a scale of approximately 330 meters per pixel. Now all we need to do is count the pixels between the clearly marked points of Kini Nui and Tahu's landing to get our distance measure. As these points are along a diagonal line from one another, this count is best done by first counting the horizontal pixel distance, then the vertical, and then using a bit of trigonometry to find the hypotenuse of the resultant triangle to get the most accurate result for the distance. Performing those pixel counts and the subsequent trigonometry, we end up with a total distance travelled of around 145.72 kilometers. That is the equivalent of Takua being drop-kicked between 2 separate cities. And remember, that is just the purely horizontal distance. Takua would actually have needed to follow an arched parabolic trajectory to achieve this flight, both because the Skybeam launch system had a vertical component to it, and simply by necessity, as he would also need to go high enough to clear the peaks of the actual mountain range that exists between his start and end points. Can you imagine the immense force that he would have needed to be subjected to in order to achieve such distance? Don't worry if not, because the upcoming section will cover exactly that, as well as other details such as the tremendous speed he would be travelling at during it, with a little help from the physics of parabolic trajectories. But first, a quick tangent. The next few equations we will need to cover in order to calculate the specifics of Takua's flight here all rely on one core measurement, the strength of gravity on Aqua Magna. And, well, that's a bit of a problem. While other sci-fi franchises often do give stats for the strength of gravity on their various fictional worlds, Bionicle is not one of these franchises. We could just assume that the gravity here is the same as that on Earth. It would certainly make for an easier calculation. However, for a story like Bionicle that includes planets many times larger than the Earth-sized robots that walk on them, that simply won't cut it here. We need to come up with a reasonable figure to use as the gravity of Aqua Magna in order to continue with this investigation, but the question of exactly how to do that has eluded me for a while now. After all, we have already covered the sizes of the bodies in the Spherus Magna system before extensively on this channel, with at least 3 different scale ranges being theorized. 2 with the Vashti and Faber sizes of the Great Spirit robot being used as measuring sticks, and 1 based on realistic sizes of what would be possible within our own universe. We could pick one of those sizes to work from in order to come up with a gravity figure, but even if we did that, there are still some unknowns like the densities of the bodies to consider, which could change the final outcome of their strengths of gravity significantly. With so many variables to consider, each one being able to produce vastly different results, how best should this problem be tackled? In the end, I decided to ignore them entirely and instead take a completely different approach. For those of you that remember your high school physics lessons, you may remember an experiment in which you timed how long it took metal ball bearings to fall a set distance, the average of which could then be plugged into this equation to estimate the strength of the Earth's gravity. It's a fun experiment to do, and one which will prove to be very useful for this investigation. If we can find an instance in Bionicle media where something of a known size falls a known distance under the influence of Aqua Magna's gravity alone, then we can measure that event to calculate the gravity field. After scouring Bionicle visual media for appropriate scenes, this sequence from Bionicle Mask of Light seemed to be our best bet. In this scene from early in the movie, Tahu and Takua plummet down a cliff face in Tawahi after going over a lava fall. In this scene, the pair are falling under gravity and the camera remains fixed compared to the background, allowing us to accurately measure the distance fallen if we can find a measuring stick to use to give us a sense of scale. Luckily, Tahu himself is perfect for this task, with the canonical height of an average Toa of 2.19 meters being used as a stand-in for his own height. Using this method alongside some pixel measurements of screenshots of this scene, I determined that Tahu and Takua dropped a total of 17.885 meters, with the drop lasting for exactly 30 frames. I used an online version of the movie that allowed me to step through it frame by frame to make the measurements, and its stated frame rate was 30 frames per second, meaning that the drop scene being measured lasted exactly 1 second. Plugging those numbers into our equation from earlier, we get an acceleration due to gravity of 35.77 meters per second squared, 3.6 times higher than on Earth. Now, of course, the rate at which Tahu and Takua fall here was determined by the animators for what looked good for this scene, and has absolutely nothing to do with any sort of canon gravity strength for Aqua Magna. But we can still do a sense check to see if the resulting measurement of 35.77 meters per second squared is reasonable given what else we know. As the size of Aqua Magna must canonically be many times that of the Earth given the canon size of the Great Spirit robot, we know that even with the lower density that a largely water world would have, the gravity of Aqua Magna should still be several times stronger than that of the Earth. With an acceleration due to gravity of 35.77 meters per second squared compared to the Earth's 9.81 meters per second squared, this measurement certainly meets that criteria. At the same time, being 3.6 times higher than the Earth is also not so ridiculously high that it would be unreasonable for beings such as Toa and Matoran to still be able to move about it, especially considering their enhanced strength and body structures when compared to humans. According to the paper Effects of Exoplanetary Gravity on Human Locomotor Ability by Nicola Poljak et al., the maximum gravity in which the average human could perform normal locomotion in would be no higher than 4 times Earth gravity, though even then that average human would have needed to undergo rigorous strength training to the level of an Olympic athlete in order to get this to work. That is a little higher than the 3.6 times Earth gravity used for Aqua Magna here, so I'd say that if a trained human athlete could handle normal locomotion in that gravity, then a biomechanical being like Takua should have no problems. Given these points, I think that this measure of 35.77 meters per second squared seems reasonable for a gravity strength for Aqua Magna, so let's use it in our calculations going forward. With that out of the way, let's get back to Takua's incredible flight. To help us determine the characteristics of this flight, we will be using the equations of projectile motion, assuming Takua follows a parabolic trajectory throughout. A parabolic trajectory is simply the path an object follows when it is moving under the influence of gravity, with said path forming a parabola, aka a curved arch, like this. There are various equations we can use that describe different aspects of projectile motion, with the ones that we will be concentrating on being those to determine his velocity at launch, the time of flight, and the greatest height achieved during that flight. From these, we can also work out additional information, such as the forces applied to his body during the initial punt from the skybeam, and in his hard landing on Tawahi Beach, as well as if it was even possible for him to clear the mountain range in his way in the first place. I do have one caveat before we go into those though. All of these equations we will be using today ignore the effects of air resistance, which would likely be significant in this kind of scenario. There are versions of these equations that take air resistance into account. However, they all rely on knowing the effect of atmospheric drag on the object in question. And while I do own a Matoran-style Takua set, I do not personally have access to a wind tunnel in which I could determine the drag coefficient of Takua. As such, we will be treating this as a spherical Takuas in a vacuum type scenario that ignores the effects of air resistance. However, given that adding it in would only make the numbers we get for things like velocity, etc. even higher, I think these figures still give us a good baseline to work from when proving this indestructibility hypothesis. Let's start off with the big one. What velocity would Takua have to have been accelerated to in order to achieve the calculated distance? For that, we need to use this equation, where v represents his velocity in meters per second, d is the distance covered in meters, g is the acceleration due to gravity in meters per second squared, and theta is the angle at which the projectile was initially launched from. We already know the values for d and g, and we will assume a launch angle of 45 degrees, as this is the optimal angle to maximize distance in these equations, so it's a good estimate to use. Plugging our numbers into the equation, we get an absolutely insane launch velocity of 2,283.09 meters per second. That is Mach 6.89. That is not just supersonic speeds. That is well into hypersonic territory, the kind of speed that can only be achieved here on Earth by rocket-powered vehicles. Now that we know his velocity, we can use it as part of these equations to work out the maximum height of his flight, as well as how long he was in the air before coming crashing back down to the ground. Let's go with his maximum height first, just to make sure he could really clear the Kauai mountain range and the Mangai volcano during this flight. Again, plugging in the numbers as necessary, we get a maximum height of 36.43 kilometers. More than high enough to clear the 33.96 kilometers height of the Mangai volcano that we calculated in a previous video on this channel. It is a little lower than the truly massive height of 38.49 kilometers that we also calculated for Mount Ihu at the time. However, his flight path does not cross that peak like it does the volcano, so this still works out. In terms of the time of flight, the numbers work out to be around 90.26 seconds in total, meaning that he flew from one side of the island to the other in only 1.5 minutes, which makes sense given his hypersonic velocity during this flight. Now that we have these amazing figures, let's take a look at them through the lens of survivability. I know we said that we would ignore air resistance, but I'm bringing it back briefly here to talk about the ridiculous temperatures this velocity would have subjected Takua to. As we covered all the way back in the Speed of the Konoe Kakama video, the air in front of Takua here would be forced up to meet his insane velocity, with that change in kinetic energy being transferred into the air molecules in the form of heat. This would raise the temperature of a thin layer around Takua's body proportional to the square of his velocity. At nearly Mach 7, that would mean a temperature of close to 3000 degrees Celsius, more than double what's needed to melt stainless steel with its melting point of only 1400 to 1530 degrees Celsius. Takua may well have been disguised as a Matoran at the time, but he did not share in their natural resistance to extreme heat. He endured temperatures hot enough to melt the mask right off his face, and yet he shows no ill effects from this. That is one point to the indestructibility argument. But honestly, the real aspect to look at is the truly insane accelerations and forces his body would have to endure here. Takua started his flight at rest, standing on the ground in the Imaja circle. The skybeam applied a force to his body, accelerating him up to his measured velocity over some period of time before he exited the beam. From that point on, the force from the beam was no longer actively being applied to his body, halting his acceleration and letting the physics of projectile motion take over for the rest of the flight. Acceleration is defined as the rate at which velocity changes over time, as shown in this equation, with its relationship to the force applied being shown by this next equation. The key thing to note here is the time in which the acceleration occurs. The longer the time, the lower the acceleration, and therefore the lower the force felt. That is why, when you accelerate a car up to say 100 kilometers an hour over the course of several seconds, the force felt is much gentler than what is felt if that same car decelerates from 100 back to 0 when you suddenly crash into a wall. The crash lasts only a fraction of a second compared to the several seconds of first getting up to speed, meaning that the acceleration and therefore the force felt is far higher, despite the same change in speed in both instances. To cut a long story short, the timing of Takua's launch is everything when it comes to determining its survivability. Given that the cutscenes from Quest for the Toa are a slideshow of still images rather than a moving video, we don't actually have a way to directly measure how long his acceleration lasted for. However, the timing between this image of the beam activating whilst he is on the ground, and this next image showing him in the air, where, crucially, he has already exited the beam, is 6 seconds. With nothing else to go on, let's say that Takua's initial acceleration lasted for a full 6 seconds. Putting that timing and the velocity figure from earlier into the acceleration equation gives us a figure of 380.51 meters per second squared. That's almost 11 times higher than the acceleration due to gravity on Aqua Magna, or almost 39 times higher than the acceleration due to gravity on Earth. For that full 6 seconds, Takua would feel almost 11 times heavier than normal due to the massive acceleration he was being subjected to. Much in the same way as you can feel heavier when you speed around the track on a roller coaster, or as fighter pilots feel when pulling high-velocity maneuvers. The force felt here is known as G-force, and, at least in humans, high Gs for sustained periods can be deadly. That additional perceived weight can have many adverse effects, with high enough Gs being able to burst blood vessels, crush organs, and starve the brain of oxygen, as the heart can no longer force blood into the head against the opposing pressure. But these are the effects on humans, with their squishy 100% organic bodies. Takua, with his 85% mechanical and only 15% organic body, should be able to handle far more of the stresses of high G-forces with likely far fewer ill effects. Though I'm not saying the dangers here are entirely negated by his biomechanical physiology. He would most definitely be having a terrible time during those long 6 seconds of acceleration. Then again, those 6 seconds at launch would be like a luxury spa experience compared to what is awaiting him at the terminus of his flight across the island. For objects undergoing projectile motion, the landing velocity is dependent upon where in the parabolic arc the landing takes place. If the landing is higher than the origin point, the velocity will be less than that of the initial conditions, whereas if it's on the same height, then the landing velocity will equal the launch velocity. If the landing point is lower than the origin point, meanwhile, the landing velocity will be higher than the launch velocity, as the object has been accelerated further by gravity. We don't have enough information to say for sure the difference in elevation between Kineinui and Tawahi Beach. However, given that the origin is partway up a mountain range and the end point is at sea level, we can safely say that Takua will be moving at least as fast as the calculated launch velocity, if not slightly higher. That means that he will be impacting the ground at nearly Mach 7, and that impact will occur over a fraction of a second, rather than the comparatively gentle 6 seconds of launch. I did initially consider throwing some more numbers at you to show just how devastating this impact would be. But, for once, I'm holding back on that. Ultimately, I think a visual aid would get the point across far better here. In the 114th episode of Mythbusters, Adam and Jamie launched a rocket-powered sled directly at a waiting car. This rocket sled was moving at 290 meters per second, 7.9 times slower than Takua's projected impact speed. Takua is the car in this scenario, with the rocket sled representing the ground, rushing up to meet him. Now imagine that, but 7.9 times worse. The car was completely obliterated by the rocket sled. So were the 2.5 centimeter thick steel plate and massive concrete block that were behind the car. Look at this image from after the impact. They're just gone. And you're telling me that Takua walked away from an impact nearly 8 times more powerful? Takua is completely indestructible. I rest my case. Of course, the question now is, just how did he gain this extraordinary ability? Is he made of adamantium? Did he have an encounter with the Mysterons? Did anyone get that last reference? Let me know your thoughts in the comments, and I hope you will join me again soon for another Bionicle Science investigation here at the Knowledge Tower.